Hey everyone, here we are 9 meetups later. So, for those of you who don't know, I'm Thiru. I am the head of artificial intelligence at Rootcode, and today we have a very interesting topic. 2 years ago, when we did our first AI community meetup, the topic was LLMs in production, right? And this was a time when LLMs were first introduced, and everybody was figuring out how we can make use of these, enormous models that are extremely powerful and seem to know everything about the internet. And fast forward 2 years later, what we have now is so good compared to what we had 2 years back. The models, the infrastructure, the libraries, the frameworks around it, to the point where whatever we had 2 years back, or the technologies and architectures we spoke 2 years back, seem primitive. And the primary driving force behind this entire transformation of LLM usage is agentic AI systems. But something that's very interesting is this is an area that we work a lot on, that we predominantly build a lot of products and solutions on, and something that's apparent is there is no one single blueprint as to how to build the best multi-agent system using LLMs. There is no commonly agreed one, it's different per use case. But in this session, we'll try to walk through what multi-agent systems are, and first of all, what agentic systems are, and our learnings and best practices and recommendations on how to build the most predictable and reliable AI systems that you can confidently put in production and serve millions of users like we do. All right, so let's taking a step back. Some time back, before this whole concept of agentic AI come up, we had a simple problem. We have a question and we have a context, and we want to pass both of these to the model, and we wanted our LLMs to be able to answer questions on data that they haven't been trained on. And so this again was pretty simple. You just had to combine it, pass it as a payload into the model, right? And then you had problems like named entity extraction, which was a major problem, let's say 5 years back, and you required days of training models. All of that got converted into a simple, 1 hour development work of connecting an API and just releasing it. But now came the problem of, okay, we can do it with one document. How can we scale this when we have millions of documents and we want to build a conversational, if we want to build a conversational search engine, how can we do it in a reliable and predictable way? Now, of course, we can't just condense all of our content and pass it through for the LLM to answer. And this is where the concept of retrieval augmented generation came in. And it was not ultra complex like developing a new type of LLM, but it completely changed how LLM systems were perceived and built. At a time where it was thought that to potentially or successfully get value out of AI, you have to have your own training, your own compute, or at least large models to a large compute infrastructure to scale your inference. Retrieval augmented generation gave us a simplified architecture that was somewhat reasonably scalable, where we were able to build knowledge agent or knowledge conversational assistant using LLMs without ever training a single model. So it was a simplistic architecture where we had the document, we slice these documents into text chunks, and we pass it through an embedding model, and we store it in a vector DB in the pre-processing stage. Then when a user asks a question, we pass the question through to an embedding model. We get we'll go through what embeddings are, and we pass it to a vector search module, and the vector search module will come up with the most closest documents related to the question, and then we generate the prompt and we pass it to the language model. But RAG was just the start. when we started adopting, and we started applying it to our customers, soon enough we realized when you give a powerful system to a set of users, of course there's an initial excitement, but the expectation only grows higher. As more models came out and as more powerful models, the models started getting bigger and cheaper and more intelligent in all scales possible, consumer or customer expectations of how models should be used also started changing. People felt that it's not enough for an LLM to just be a retrieval augmented encyclopedia where you can upload document and ask questions. They expected their LLMs to be able to perform actions, take and do actual automation like a human. And this is where retrieval augmented generation started having its series of problems. Now the first problem is vector DBs can be highly inefficient when it comes to capturing meaning in a scaled context. Now just going over what vector DB vectors and embeddings are. Embeddings are a very simple concept in which you use an embedding model. So this is an AI model where you pass in the text and you get a bunch of numbers outside which is supposed to represent the meaning of the text. And like we saw in a typical RAG architecture, what we would do is we have the document context vectors. So we will embed the documents and put it in a two-dimensional embedding space, and we embed the question as well. Now everything is in text, by the way. Until this point we are dealing in the realm of text, and we find the context or documents or pieces of text that are closest to the question which we think might have the answer, and pass both to the LLM. Now one rare problem with embedding models is also that they are very dependent on the construction of words that make a sentence. For example, in some scenarios, and this has been proven a lot of times, the word non-dairy products is more closer to milk than to apple. This is because the word non-dairy itself has an association to dairy. Right? So these types of problems prevented RAG applications from scaling. And when it comes to vector databases, not all data has to be vectorized as well. It made sense for us to vectorize text data because it made search so efficient and it enabled us to quantify search. But let's say you have structured data, or you have data stored in a database table. You don't necessarily have to take a dump of all of that, put it in a vector database and index it, right? We already have solved the problem of querying structured data efficiently, and it's called SQL, and there are multiple SQL engines that you can openly use. So the RAG architecture in a way compressed all sorts of data into being used by vector databases, and that became a serious limitation. And the problem is also that if you have a vector database which is static, most often the inputs aren't dynamic. When you update your primary data source, let's say you're trying to vectorize an entire database, whenever your database gets updated, you need to vectorize and build a pipeline to store it in your vector DB as well. And this became really messy and chunky over time. Now the second problem is every aspect of response formulation is fully dependent on the LLM. Now if I think at this point almost all of us know how LLMs generate the text. They just predict the next tokens. Even the most advanced or intelligent of LLMs are trained in different ways, but fundamentally if you look at the output layer, they predict next tokens. But that's not how math is done. That is not how calculations are done, and you do not always have to rely on the LLM to generate mathematical constructs. So when it came to deploying the LLMs or these types of non-trained large language model systems in production, it became very unreliable because now you just have to ask the model to be accurate and pray that it is. And it doesn't make sense for an LLM to generate this as well. Like you can just call a calculator, and this solving math is a problem that, I mean, most calculations at least, it's something we have already solved. And it also again brought it down to this limiting factor that any LLM app in a RAG architecture is only as good as its vector retrieval. And the third most important problem is the RAG architecture is only useful for information retrieval. So you can't do, it can't do anything else. I mean, you can't go to ChatGPT, maybe with operator you can, but the previous versions of ChatGPT, and ask it to send an email or plan your project and send it as a report. It wouldn't be able to take those actions or go ahead and execute those tasks. Right? This is where the concept of agentic systems came into play. Now, the very first LLM agent systems flipped the paradigm by saying, okay, we'll use the LLM to only what it's good for, which is understanding dynamic information or instructions in text, and then being able to plan and decide again in text on what it should do. For any task that it can't do or that it shouldn't do ideally, let's use tools. Let's just call endpoints, let's call functions, let's call calculators. And this is where frameworks like LangChain and LangGraph also started coming into play. And the tools in turn will give feedback to the agent on whether it has achieved its goal. Now, if we look a bit more deeper into the anatomy of an agentic system, the fundamental principles of it, every agent has a goal. Now, the goal defines what the agent is supposed to do, what its purpose in the system is, and the goal only focuses on that, and the goal also defines how it judges that it has achieved the purpose, what is the success criteria. Right? Now, this can be making a reservation, planning a route, creating a financial statement, and auditing it and clearing out everything. So, this framework condensed most of the problems we had with a RAG system by giving agents specific goals, and the goal isn't just to return a response to the user, it is to achieve a specific task. Then we had tools. Now, tools are, again, like I said, it's external functions or APIs the agent can use to reach its goal. This can be a calculator, this can be for a database querying, you'll connect it to a querying endpoint, or it can even be another LLM. And then there is memory. Now, this is what distinctly separates RAG systems from agentic AI systems, because in a RAG system, you just have to remember the user's conversations, the requests and responses, what the user has said, what the bot has said. And it's relatively straightforward to do. And with modern models with massive context windows, it's not a massive challenge either. But when it comes to agentic systems, you need 4 different types of memory, or your LLM agent should be able to, at any given point in time, return these 4 different types of memory to be able to function effectively. So, one is procedural memory. Now, procedural memory is it needs to remember how it should execute a task, or what sequences of steps should it take to reason on how it should break down a task, so that then it can go ahead and call the necessary tools to execute. Then there is episodic memory. Now, episodic memory purely focuses on prior decisions taken, what was the probability of those decisions, why it took those decisions, and this is on an on-demand basis fed into the inference pipeline as well. Then there is session memory. This is shared with RAG systems as well. Session memory is basically the conversations, the history of the conversation that happened. And then there is semantic memory. Semantic memory is the LLM's pre-trained ability to solve certain problems. Now, this can be generating code, this might be something like generating human-like responses, or being able to break down the task and retrieve the right information. So, semantic memory is not stored anywhere in our system most often. It's the memory it has gained by the large-scale training it has gone through. Then we have guardrails. Now, guardrails is also a common factor, but when we scale from an agentic system to a multi-agent system, guardrails become pretty sophisticated and complicated. So, without guardrails, you simply pass the prompt to the LLM and you hope the output is good. With guardrails, we first filter whether the input data contains any sensitive information, whether we have any conversations that are seemingly going off topic, jailbreak attempts, and we try to protect the model so that it doesn't hallucinate. Now, putting this all together, this is how a single agent system would look like. You have the planning aspect of it, where you ask the model to do multiple tasks. When it comes to planning itself, first it needs to be able to plan and break down as tasks on what APIs and endpoints it needs to call, what are the parameters it needs to pass to the functions. Then it should be able to reason through that, and it should be able to decompose the reasoning as well if needed. Then we have the tools. Now, in this particular scenario, we have given it access to a calendar, calculator app, a code interpreter, and a search function, and more. And based on the scenario, it will have to use one or more of these tools. And then we have long-term memory, which go into the instructions themselves of what the agent is supposed to do. That's where the goals are defined. And then we have short-term memory, where it has to remember the context of the conversation. But single agent systems are not perfect either. When we evolved to this stage, we realized, okay, this is very expensive, because all of what we saw here has to go inside the prompts. We have to define functions around it. Function parameter parsing happens through the prompts, and this led to massive token consumption, and it was definitely a lot more expensive, and that increases the cost of processing as well. And that in turn also increased latency, because now the model can take a massive context window, but now the model takes 15, 20, 30 seconds to generate a response. Even if you use features like streaming, where you on an on-demand basis get the tokens in a stream, it still slowed down system performance, and when you have like a 15-second lag, your API connection won't sustain that long. So then it started causing production failures. And one of the main problems is called attention dilution. Now imagine you just wake up one day and you try to think of everything you have to do that day as an instruction, and you try to remember it at every given point in time throughout the day. That's not how we work, right? We focus on specific aspects, or when we are about to do a task, we focus on the info. We try to retrieve from our brains on what information do we need to execute and complete the task. But when you pass a massive prompt to an LLM that says all of the complex instructions of how it needs to function, it ends up generating super general answers, or in an agentic system sometimes even does nothing, because its attention of what specific skill or area is necessary for a particular task is diluted because it has to retain everything in memory. And another major limitation is that we are limited to one LLM for all tasks. So we have, let's say, if you have a single agent system, if the purpose is to have human-like conversations, you use an OpenAI model or a DeepSeek model, whereas if it is for code generation, the state of the art is Claude. And this is exactly where multi-agent systems started to come up. So the idea behind the multi-agent system architecture is that if you can simply isolate different agents, give them particular tasks to do, and then figure out a way to make them communicate with each other, then it solves almost all of the problems that we spoke about earlier. Attention dilution is not a problem, because your agents are only focused on doing what they should do. And then you have a task breakdown agent that purely focuses on what is the execution strategy. So let's say you get an input, it passes it to the right LLM and gets a whole task breakdown of what's happening. And then we have the tool cluster. Now the tool cluster is again a set of functions, but this time instead of one agent calling it, there are multiple combinations of agents calling the tools on demand. And then we have a common data access layer for all the agents. So, for example, we have the data sources, and we have a CRUD API layer. We have for FAQs, we have a vector DB for agent configuration and orders and purchases. We have a SQL database, and all of this is layered by a common data access layer. This sounds very simple, but this is one of the hardest things to do when developing a multi-agent system, purely because of the fact that when your API endpoint changes, you have to go ahead and change your agent configuration too. But there is an interesting solution to this, which we will get to next. Now, if we put it all together, user sends a input, it goes to the input guardrails. Then you have the task breakdown agent, which will create the execution plan for the on how we are going to tackle this particular inquiry. Now, this is in a chat context, but this can apply to even generating code or taking actions too. And then your agents call the right tools, your tools call the shared database layer, and we are able to delegate some responsibilities here and solve the cost, inference and scale problem too. Now, these systems as by themselves aren't optimized for production. Now, of course, we can develop something like this, test it with a few friends, test it with a few hundred people, maybe 500, 1000. But when you scale to 1,000,000 users and there is so much activity happening between the LLMs, it's super important on how you orchestrate message passing and memory. But because in here now, earlier only the agent had to handle its memory. Now, an agent has to handle its memory and other agents' memory as well, so that it knows what's happening and how the state is being changed. So, how can we optimize tools for production or multi-agent systems for production? It first starts with optimizing the tools. Right? So, how can we optimize the data access layer in a way where, regardless of how fast our data sources are changing or how our user base is changing, our system doesn't fail. That is where the concept of Model Context Protocol, or MCP, comes in. Now, MCP, it's finally dubbed as the USB-C for AI agents, is a common shared protocol introduced by Anthropic early last year on connecting systems, agentic AI systems with applications. Now, MCP has a whole host of tools, and it's an early protocol, so people are still working on it. We integrated it in a lot of projects as well. The fundamental concepts are there's an MCP client and an MCP server. Now, let's say you are an IDE, if you are VS Code. As the developer of VS Code, you will create an MCP server which has the entire configuration of APIs and functions and features you can call within VS Code, and you just expose it as a server. Now, if I want to build a tool that controls VS Code and that interacts directly with VS Code's functionality, I will develop an MCP client. Now, I do not have to know about how VS Code's APIs work to develop this, so because it provides a shared middleware access layer. And inside the MCP server, you have the tools, you have the tool configurations, and then you have the resources which are accessed using the tools, and then you have predefined prompt templates as well. For example, if I am asking for let's say generate me sample data payloads, then you output it as JSON. And the first problem it solves is it provides a standardized communication layer. It provides a unified protocol, meaning servers can be developed, and consumers do not have to, or developers do not have to worry about how they are, what APIs their agents have to call exactly. And from a server MCP server developer point of view, if I own a product that I want to be able to be used by LLMs or agentic AI systems, I can just define my APIs there, and when I change the configuration of my endpoints, or when I change how data access is done, the MCP middleware automatically streams that message to all connected MCP clients and instructs on how you need to change your input output parameters to be able to handle the change made to the data service. So this is sort of like the GraphQL movement for AI, where you do not have to worry about what the specific endpoints are, how they are designed. Your LLM agent agrees with the MCP server on a API contract. And then there's dynamic tool discovery as well. Instead of hard coding the tools, it's the MCP server which exposes the tools available to your agent. So you do not have to go ahead and figure out, okay, how am I gonna, let's say, generate code or update code in real time through VS Code, or if your goal is to work on GitHub, then how am I gonna create a pull request through the GitHub APIs? The MCP server client contract automatically dictates that. And then you get the proactive schema updates as well. Whenever your API schemas change, your AI servers or your client servers are consistently notified of it. So overall, MCP provided us with this REST or GraphQL-like framework where data providers or data owners or platform owners, let's say if you're Figma or VS Code or GitHub, you can build your own MCP server, host it, and any LLM or agent which wants to use your software has to just agree with it. This is really important because only now or only for the next few years it's going to be majorly humans using tools and software. There's going to be a time very soon where a lot of AI, at least a significant percentage of requests or traffic in the internet is going to be through AI agents because they work really fast and there's going to be so many of them. And MCP provided us with this nice framework through which we can integrate with data. Now the second problem in getting to production is, how do you know your LLM is working fine? Now let's say you are building a conversational AI assistant or a code assistant or a design assistant plugin for Figma where you just want to describe your design and produce the UX designs of it. How can you test it, right? How can you quantitatively evaluate that your system is performing well? Most often, when we try to condense LLM systems into quantifiable or quantitative variables, it doesn't scale very well because the entire intelligence factor of LLMs is subjective. It is not super quantitatively evaluatable unless you do millions of tests. That's where LLM evals become really important too. So it's super important if you're developing a production application to have this in your CI/CD, and there are frameworks like deep-eval which can help you do that too. So some of the most popular ones are geval, deep acyclic graph, and Regas. So you can just go and read about them. They're just different directions or different aspects of evaluating an LLM's performance and reasoning capabilities. When you go to the LLM evaluation pipeline, the common best practice is we have a human preference data distribution, meaning we generate a distribution of conversations and answers and memory states. We pass it through a sampler and then we calculate the metrics for it. Now, most of these approaches are LLM as a judge based, meaning you use a supervisory LLM, most often one of the top tier models, to evaluate the quality of reasoning. Now, is it super quantifiable? No, but is there a quantitative metric to measure the quality of reasoning? There is no perfect one either. So, since modern LLMs are really good at reasoning, using them works really well when developing applications too. And then comes LLM observability. Now, the tricky part, if you've ever built a LLM system, is when your customer asks, how much is it going to cost me? Right? on a normal scale, if you're, let's say, you're developing general software for the cloud, it's somewhat predictable. Again, it's if you're using an elastic system like AWS, it's going to be based on users. But if you're building LLM systems, it's going to be based on the prompts, it's going to be based on the context window usage, how much your users are using it, how are they using it, even if your user base stays the same, or what type of data is being updated that the LLM is referring to. And the best time to integrate LLM observability into the project is as early as possible. So we use one of the most common frameworks we use is LangFuse, but there are a lot of other ones too. But it's important from a very early stage to visualize both from a cost and economical direction, and also from an evaluation direction on how your LLM's performance increases or decreases with every change you make or every data source you integrate. Now, all of this being said, most modern LLMs we work with, or the proprietary ones at least, open source one, of course, we can play with the weights, but for economic deployment of LLM systems, it's text. For most systems, it's text in, text out, and most of the performance or accuracy in the LLMs can be unlocked by optimizing prompts. But if you have developed LLM systems, you will know that prompt optimizing becomes a funny game, where you will have to hopefully go ahead and ask the LLM nicely or even emotionally blackmail it, and to get an accurate output. And by the way, the emotional blackmail works. People have tried it, and there's like existing research. But how can we avoid this constant LLM pleasing? Right? We definitely need a better way than to pray to the LLM gods. And another solution to this potentially could be framing this problem differently. And that's where the thought process of training prompts, if we could train prompts like we train models, comes into play. Now, going over how a basic neural network is trained, we have a forward pass. We have a set of neurons. So in the forward pass process, our inputs go through the input layer, hidden layer, and output layer. Weights are calculated, and initially the model outputs garbage. And in most modern models, we have like trillions of parameters, weights and biases. And then over time, in the backward pass, we get a loss. We calculate the loss, which basically says how bad the model is, which is a quantitative variable of what is the average costs of the training data, like how wrong it is. Then we calculate the gradients. Now, for people who are not very familiar with the mathematics of gradients, gradients are simply a way of telling your LLM, of telling your model how wrong it has been and by how much should it update itself. Or in other words, by how much should each weight be increased or decreased to slightly nudge accuracy to be more towards our favor. So this is the feedback mechanism to the neurons. And now each neuron will have some degree of increase or decrease during backpropagation. And then we go ahead and update the weights. So we have this is just the equation. So dj over dw is basically we differentiate with the cost with respect to the weights, and we calculate the gradients, and we make the gradient update. So I mean, this is a mathematical equation, but simply we just calculate by how much we need to update the weights, and we go ahead and update it. The next question comes in: what if we could backpropagate through the LLM prompts itself? Now, of course, training an LLM or fine tuning an LLM is one part, but if we can start framing a problem, a problem of optimizing prompts by treating prompts like weights, we might have a direction here. And this is where the idea of self-optimizing prompts or the research framework around text gradient descent comes into play. Let's take an example system. We have a query agent that takes a question and generates a database query. We have a database tool which will take that query, execute the query, and then we have a response agent which gets the data payload from the database which is a result of that query, and crafts a somewhat useful response. Now, if we walk through this, if we think of the forward pass, the customer asks or the user asks, what's the shipping status of my order 1, 2, 3, 4, 5, and this is how the query agent is structured. Now, this is very simplified to understand the concept. You're a database query assistant, given a customer question, generate the query. Query agent outputs the prompt, and the database tool returns the result, and then we pass it to the response agent. The response agent gets the question and the database results, and we get the output. Now, similar to how we calculate how bad our model performed, we use an LLM as a judge mechanism to score the output and get a text feedback on how bad the response was. And this is similar to our loss computation step. Now, then comes the backward pass, where we have to calculate the gradients. Now, if we on a very conceptual level, if you think about the gradients are basically feedback to the weights on how they should update themselves. And in the backward engine, what we do is we create this sort of LLM system where the feedback is the prompt doesn't include the tracking information or how to track shipped orders, and to enhance the prompt we need to direct the assistant to provide tracking details. Now, this is for the response agent, this is for the outermost agent, this is the feedback. Now, then we propagate the feedback to the prompts of the DB tool as well. Now, of course, similar to training neural networks, where not all parts of the neural network system are differentiable. There are parts of neural network which you can't differentiate through. You can't differentiate through an API tool. So, you go to the agent that generates the query, and it says, okay, enhance the prompt to specifically direct the assistant to provide tracking details. And then you take it to the query agent, the middle agent which generates the SQL query themselves. Then you explicitly say the problem with the prompt is it's not explicitly fetching the tracking number. Now, this backpropagation engine in and of itself is an LLM agent that is working. Now, that is commenting on how different parts of the other agents' prompts could be improved slightly to get a better result. Now, we generate for the query agent, and then now is the time to go ahead and update each prompt based on its textual gradient. So, you pass the updates, you pass the prompts, and you simply improve the prompts. And when you update the query agent, we ask it to always include tracking number and tracking URL fields, so that in the SQL queries we are requesting for those fields. In the response agent also, we are go ahead and saying, okay, when you get that data from the SQL database, always include the tracking information in your response and explain how the customer can track their packages. And then you run the update, and then now comes the second forward pass. You have the update, and now the new query agent outputs tracking number and tracking URL which weren't there before, and you have the new result for the database from the database. And in the new response agent output, you have the tracking number and tracking URL. Now, this is a very condensed, and in the new evaluation you get 10 out of 10, a perfect score. This is a very straightforward example of how this could work, but this is super potential when you are developing complex agentic systems, because now you can create this cyclical auto optimization system where you of course rely on an LLM, and that training process itself takes time. But instead of us trying to go ahead and nudge prompts here and there, in the middle change words, ask for help, use a bit of emotional help, we let another agent do it. Now, this can be a black box agent, or we can build our own models to do it as well. So, those are some of the strategies on how these multi-agent systems can be put in production. And what's very interesting is, for the first time in the history of AI, we have systems that can take a loosely defined goal, self-organize, and execute a given set of tools. And it's going to be limitless on what we can build with these self-driven systems, and it's going to completely transform how software is being used, where there will be interfaces or API, at least on a back-end level, interfaces being made for agents to optimally access as well. And it's going to be super cool on what we would be able to build in the future. Thank you.